Okay, so today we're going to talk about the second part of the memory system, and we're going to focus on the declarative memory, and we're going to touch a little bit upon the semantic memory aspect as well. Okay, now let's take a look at the memory system. Last time we talked a lot about the sensory memory, the short-term memory, and also the working memory. Now, today we're going to talk mostly about the long-term memory, and we're going to focus on the declarative memory. You might also know it as the explicit memory. And we're going to talk more on the episodic memory. We're going to also touch upon the semantic memory. Okay. Now, what is declarative memory and the aspect of this episodic memory? Okay, so this is really regarding about the memory of specific events. And so it does not only refer to like specific time and places, but also what happened during that time. And then also the location. So you kind of want to think about it as a recollection of a certain experience, if you will. And so then what happened is that the memory of the episodic memory, episodic events is not only specific to time and places. It's also largely is very specific to individuals. So you can see that these episodic memories are very individualized based on the person's life experiences. Now, this is the anatomical schematics that are involved in the episodic memory. Okay, so the most important structure that you'll need to know is the hippocampus. Okay, and now this is something you probably learned in your Psych 243 that hippocampus is one of the most important structure when it comes to learning and memory. And later on in next lecture, we're talking about the physiological mechanism why this is the case. But for now, just remember that hippocampus is at the central for episodic memory and also more largely on declarative memory. And so hippocampus, when you want to kind of think about it, is the hub that really allows this to happen. Now, information, so that's it when you have experience. And then the information is going to come through like many association areas. And then part of it is going to go to the perirhinal cortex. Another part of that is going to go to the parahippocampal cortex. And these areas are all considered um, medial temporal lobe structures. And so these medial temporal lobe structures, two of them, the perirhinal cortex and the parahippocampal cortex, is going to synapse onto the entorhinal cortex, and the entorhinal cortex is going to project these information to the hippocampus. Now, hippocampus is really where the consolidation of memory occurs. Okay, and then you'll see that after the hippocampal formation forms these kind of memories, and then now it forms it in various type of ways. It may be formed in a new synapse, and it might be actually formed as you see in dentate gyrus, a formation of new neurons that happens there. So there are adult neurogenesis that occurs at the dentate gyrus, and then these new informations are going to get then kind of projected through the fornix to the mammillary body, and then all the way to the anterior thalamic nuclei, and then some of that is going to either come back to the hippocampus, and then some of that is going to go to the temporal cortex where the more permanent bases of memories are formed. And then now you see that one of the structures that you see that has a lot of mutual connections to is the prefrontal cortex. And that gets projections from the thalamus, that gets projections from the hippocampus through the fornix, and also gets from the entorhinal cortex, and also from places like the perirhinal and the parahippocampal cortex. Now, all of these are the reason that the prefrontal cortex is really important for well, we kind of want to think about it as the actual consciousness processing of many things. And so later on, we'll talk more about the prefrontal cortex, but now just kind of know that this is the anatomical schematics when it comes to the structure that are involved in memory formation, okay? Now, a lot of the structures in here are called the medial temporal lobe structures. And now, if you were to take a look at the actual cross section, and then these are the structures that you'll see. So the hippocampus, the rhinosulcus, and so now let's take a look at these structures close up, and you see the hippocampus in blue, and then this thing that looks like that, that's the hippocampal formation, okay? And then you'll see that there is the entorhinal cortex, and then before the entorhinal cortex, there are the two structures that we talked about, the perirhinal cortex and the parahippocampal cortex. In these two areas, they are going to send their synapses to the entorhinal cortex, and then the entorhinal cortex then is going to send its information into the hippocampus. Okay, and then later on you'll see that the hippocampus is going to send its information to the thalamus somewhere there. Okay, so basically you will see that this is a major loop that is going to loop back and forth. Okay, and then of course the thalamus is going to send its information to the lateral temporal lobe, and then this is going to then come back, you know, it's kind of pretty much the same way of what we said in the previous slide. So what happens when you have damage to the medial temporal lobe structures? Well, then what is going to happen is that this person with damage to the medial temporal lobe is going to suffer a severe form of anterograde amnesia, which is the inability to form new memories, okay? And then, so this is the case of HM. He has very severe form of epilepsy, and in order to control his seizures, the doctors recommended bilateral resection of the medial temporal lobe structures, which is where the epicenter of his seizure is coming from. And then, so this included the hippocampal formation, also the parahippocampal gyri. And then what happened is that his seizure really did improve, but then his memory suffered as a result. And then, so in this case, he was able to, in his case, he was unable to learn new facts or recall new experiences. For example, when given a list of 4 words to remember, he was able to correctly recite them back immediately. Now, within 5 minutes, however, he had no recall of any of the words, even with hints. Okay, and then he was not able to remember being even given a list in the first place. Now, by contrast, his memory of remote events from his childhood and up to several years before his surgery was intact, which means, so this is what the term is called retrograde. Now, what happens if you have retrograde amnesia? You will not be able to remember childhood stuff, or like the whatever that happened before the surgery. Okay. Now, however, so now this is not HM's case. He has no problem remembering things from his past, but he has problem learning new material. Okay, basically. And so now what the case with HM is he has no recall of events that happened from his surgery, basically. Now, despite his profound memory deficit, HM's personality and general intelligence test that is looking at his IQ were pretty normal, okay? And now, in addition, he retained the ability to learn several tasks that did not require conscious recall. And now, so for example, his performance on like a mirror drawing task improved on successive days, similar to like normal controls, despite his having no recollection of doing the actual task on the previous days. Now, but so this is looking at a procedure memory. So this has nothing to do with the ability to learn new information. Okay, and Now, similarly, when primed by exposure to words such as absolute and asked to complete the stamp absol, and then he chose the word absolute and that he has seen previously at a higher than chance levels, despite having no conscious recall of seeing the words before. So this is the another aspect of memory that they were testing with the priming effect. Okay, so that is a more implicit form of memory, which has nothing to do with the declarative memory that we're talking about today. So uh, all in all, what I'm trying to tell you is basically is that HM's cases is very severe only when it comes to episodic memory, when it comes to the declarative aspect of memory, and on top of that, he had the severity not coming to the retrograde amnesia, but what kind of comes to the anterograde amnesia, which is the ability to learn new information. Okay, which what does that mean? That means that this hippocampal regions, including the parahippocampal gyri. This is very important for learning new memory and also memory consolidation. Now, the patients that had both sides of their hippocampal region removed really have a very bad case of uh, interrograde amnesia. Okay, and you can see that this is the case in the digit span test. Okay, and then when they do the repeated trial, and you can see that the controls do really well. So the x-axis what you're seeing is the number of digits in the memorandum. Okay, and then in the y-axis what you're seeing is the mean trials to criterion, which means that how many successive times do they have in order to go on to the next um, number of digits. So you can see that the controls do really, really well. And the patients with the bilateral hippocampal regions removed, they can kind of remember up to 6 digits, kind of similarly to the controls. But after that, their number of digits in the memorandum it just escalates a lot, and they cannot learn this very well. And up to 12 digits or so, and then what happened is that the mean number to trial to criterion really is suffered, and they cannot do any more after that. And so what happened is that the controls, what you see is that they learn over time about like 11 times maximum to try, but then the patients takes more than 25 try and cannot exceed digits over 12 in a chain. So the problem with the bilateral hippocampal removal really has to do with the fact that these patients cannot form the memory very well, despite having repeatedly presented these informations to them. Now, one of the ironic thing with when it comes to uh, HM's lesions in the hippocampus is that not his entire hippocampus was removed, because when you look at the anterior part, you can see that there are hollows here, right? So that's where the lesion or the surgical removal of his hippocampal region was. So that's in the anterior part, but in the posterior part, what you can see is that these parts are all still present. Okay, now the thing about this that is so interesting is that it turns out that it's more likely the connections from the parahippocampal and the entorhinal cortices were severed rather than rendering like non-functional. So it turns out that these projections that is coming from the parahippocampal and the entorhinal cortices are very important and that projects to the hippocampus rather than the hippocampus itself. Okay, and which kind of makes sense given on the loop the anatomical loop that we were looking at the very beginning of this lesson. Now, in animal models, how do we do animal testing, okay, of memory? Well, so there is something called a delay non-matched sample task. In this task, what they do, they usually do this on monkeys, okay? So, and then what happened is that the monkey is originally presented with a sample object, what you are seeing in here. Okay, and then when he displaces it, then he finds a palette full of that is beneath that. Okay, and then they can vary, so they can vary the delay kind of that. And then if they were looking at a very brief delay, then they were looking at more like a short-term memory aspect. If the delay is very long, then they're looking at longer term delay. Okay, and then now after a variable delay, the monkey is presented with the original object and another object, basically. Okay, and then now basically what the monkey has to remember is that, okay, I have already eaten the food that is underneath the original object, in this case the key. Then the food palette is now must not be under the key but underneath the novel object. Okay, and then what happened is that the monkey, they'll learn that the food is always presented under the object that differs from the sample. Okay, so basically, so this is why it's called delay non-match the sample task. Okay, and what happened is that the monkeys with normal intact brain, they do pretty well, so you can see that the percentage correct are all around 90% when it comes to the actual success rate. Okay, now what happened with the animals with the hippocampal lesion, you can see that they don't do very well. So with the lesions, their correct rate kind of goes almost down to the chance level when you look at the 2 to 10 minutes delay. Okay, so what this is basically saying is that the hippocampus is a very important aspect when it comes to the not only the formation of the memory, but also kind of like the manipulation aspect of the memory as well. Now, when you think about the actual medial temporal structures when it comes to memory formation, the other structure that you usually think about is the amygdala, other than the hippocampus. And now the role of the amygdala in memory is more like it's to modulate the memory. Okay, so what you have is you will have an experience, and then this experience, depending on how emotionally arousing it is, um, maybe it's a very dramatic thing that you will remember. Maybe it's something that's very, very happy, and then let's say your graduation or something, or your wedding, your firstborn, all of these, what that's something very sad, let's say passing of someone that you love dearly. So all of these are going to generate a very emotional aspect of you. And then what this is going to do is this is going to release a lot of adrenal stress hormones, and then this is going to activate the non-adrenaline release. Okay, and then now this is going to happen a lot in the amygdala, in the basolateral portion of the amygdala, and through that, then you'll see that the amygdala and the hippocampal regions, they are reciprocally connected. That may be important for emotional aspect of memory. So what happened is that this is going to modulate the memory of consolidation, and then this projection from the basolateral amygdala is going to project to the hippocampus, and then there is also going to modulate uh, the memory storage when it comes to the cortex aspect. Okay, and then so what you see that the amygdala has been demonstrated to be involved in fear memory and also in modulation of effect of arousal on memory strength. Now this is something that we'll cover in the emotional lectures when we talk about fear conditioning, but today just kind of give you a little um, a little like what is about to come in the next lectures. Okay. Okay, so the hippocampus and the amygdala are the medial temporal lobe structures that are involved in memory. And now let's talk about the diencephalic structures that are involved in memory, and that's the thalamus. Okay, so the thalamus, there are two thalamic nuclei that are critical for memory function. So one is the anterior nuclei, and that is gets its projection from the hippocampus, and from the fornix and then to the mammillary body, and from the mammillary body, and then it gets projected to the anterior nucleus of the thalamus. Okay, so that's the first thalamus, thalamic structure, and the second thalamic structure is the dorsal medial thalamic nuclei, and that gets its projection from the amygdala. Okay, so both of these. So when you kind of think about this, this is like the parallel structures that are kind of like the parallel processing that you see in the vision as well. So there are two separate and yet interconnected streams that are really processing both aspects of the memory. Okay. Now, when we so now let's talk about what you should stop drinking now, basically. And this is so now let's take a look at the two brains. On the left brain, you have someone who does not drink much, okay? And on the right brain, what you're seeing is a person that is an alcoholic, and they're both 43 years old, okay? And you can see basically that the left brain looks like it does not have a lot of very prominent gyri. The the ventricle structure is not very big, and then as opposed to the ventricle structure here, it's very small. Okay, now and when you look at like the actual gyrus here, you can see that there isn't that much cortical tissue that's missing compared to this person. Okay, so when you kind of look at these alcoholic brain, you really kind of think that, well, their brain matters, the gray matters really are very, very atrophied. Okay, so you can see that look at the atrophy also on the diencephalic structures here. Okay, so you can see here and versus that is a lot of atrophy in there as well. And as we said, we see a lot of cortical atrophy, and then now you don't see it that well here, but in the alcoholic brain, you will also see some atrophy in the mammillary bodies as well. Okay, now, so this is a condition called the Korsakoff syndrome. Okay, and so this is caused by the deficiency of thiamine, which is vitamin B1, due to a lot of drinking. And then they're going to have a lot of anterograde and retrograde amnesia. And they're going to have something called a confabulation. Now, pathologically, these patients have bilateral necrosis of the mammillary bodies and a variety of the medial diencephalic and other periventricular nuclei. And then what happened is that acutely, these patients with B1 deficiency have a triad of ataxia. So that's the first condition that they'll have. The second condition they'll have is eye movement abnormalities ranging from gaze paralysis to nystagmus. So, and then which is like a vision condition that the eye makes repetitive uncontrolled movements. And then the third one is a state of confusion. Now, the severe cases can really result in coma or even death. So now the patients that survives the acute stages of the B1 deficiency are left with anterograde and retrograde amnesia that we talked about here already, and this is caused by the bilateral and diencephalic lesions. Now, as you saw in the previous slides, they also suffer from some frontal lobe dysfunction, and because their their cortex is very it's really atrophied, right? And then so this is going to result impairment in judgment, initiative, impulse control, and sequencing tasks. Now, one of the things you want to know is that unlike patients with a pure diencephalic lesion, the Korsakoff patients tend to confabulate. Okay, and you're probably thinking, what is confabulation? Well, confabulation is these patients like to provide spurious answers to questions rather than saying that they do not remember. So, this is caused basically, this is basically probably caused by like related to things like the frontal lobe dysfunction, which causes the disinhibition and a loss of self-monitoring capabilities. Okay, now in on top of that, they're also going to have a lack of insight, which is associated with the loss of the central medial cortical structures that is in the prefrontal lobe, in the uh, in the um, in the central medial or cortical structures. Okay, and then they are also going to have apathy, which means that they're going to have a lack of interest and they basically become non-responsive to a dramatic change. So if you tell them something about like a major disastrous news, and then they're just going to respond to, is that so? So that's something that is not very good when it comes to the actual cognitive capabilities of the Korsakoff syndrome patients. Okay, now we have talked a lot about the medial temporal lobe, and we have talked a lot now about the thalamus and the mammillary bodies due to thiamine deficiency. Right now, let's talk about the next structures that are very important for episodic memory, and that are the neocortical structures and the basal forebrain in the memory function. Okay, now the best example that you see is this is the Alzheimer's disease, which is mainly a cortical induced like memory problem. Okay, memory disorder. And then another one is Pick's disease, which you guys might also know as the frontal temporal dementia. Okay, now these structures that are involved in memory functions are the lateral temporal lobe, the dorsal medial prefrontal lobe, and the medial central cortical structures. Okay, now the things that kind of so those are the cortical structures, and then the structures that are involved when it comes to the basal forebrain, these and that are these structures. That's the nucleus basalis of Maynard. This is comes from within the substantia illuminata, and then the next one is the diagonal band of Broca. And then the next one is the medial septal nuclei. Now, all of these are the major cholinergic sources to the brain. Now, one of the things that you have heard about with Alzheimer's disease, that it seems like this Alzheimer's disease problem is like that they lack abilities to produce enough acetylcholine in the brain, right? And then in many ways that is correct. Okay, but you see that Alzheimer's disease has many layers, and then so today we'll talk about them in various aspects. Okay, now the frontal cortical areas are, now let's talk about each and every one of them and what it does. So now when it comes to the frontal cortical areas, the left inferior dorsolateral prefrontal lobe is very important. And because this has to do with the semantic retrieval. And also it has to do with the temporal sequencing, and also very important for the meta memory, which is one's own knowledge and report of that memory. Okay, now confabulation is something that we talked in the previous slides, but this is basically results from the prefrontal lobe damage or the dysfunction of that. Okay, and then so confabulation, a lot of it is that instead of patient cannot remember something, they just they now a non-confabulating patient would just kind of tell you exactly that I don't remember this. Okay, but confabulation memory, they'll kind of tell you a false biographical or an event memory. And so and this has nothing to do with the fact that they're pathological liars. They the people that are the patient that are confabulating, they don't even know they're lying. Okay, and so what happened is that they just kind of tell you, they just pull something out of thin air and tell you a false memory. And but at the time they're telling you, they actually really believe that this is true. Okay, but when you ask people that are close to them, and you ask, let's say his or her significant other or spouse, and you'd be like, did this really happen? And then it's gonna, and then the spouse is gonna tell you, no, that did not happen. Okay, so the confabulating patients, they're going to give you a lot of false memories. And not only the fact that they'll tell you a false story about themselves, there are very little self-monitoring, and then they'll also have false recognition of something that did not happen, basically. And in order to also kind of tell if this is a true confabulation, is you can ask them to sequence something that, if, let's say, if you, for instance, you tell them a story that happened of, let's say you tell them that, okay, this person is going out to buy something, and then so the first thing, he grabbed his wallet at home, and then second thing, he opened the door and left his house. The third thing, he got into his car and then drive to the store, and then the fourth thing, he bought something at the store and then returned home. Okay, so that's a sequence of something that came, that is the story. And then if you ask the confabulating patients to kind of give you this back, this exact sequence, he will tell it, all these temporal events will be out of order in his mind. He'll tell you that, okay, first he got on his car, and then he got his wallet at home, and then the fourth, and the next thing that he did is that he bought something from the store, and then the last thing is that then he opened his door at home. And then so you'd be like, but that's not even logical. Well, confabulating patients uh, basically really do not have a very good logic in their mind. Okay, so this is one of the hallmark when it comes to the confabulation, is that they will just tell you a bunch of things that in many ways do not make sense, and then are regarding false memory. Now let's go back and talk about the basal forebrain structures. And the basal forebrain structure really provides a major cholinergic input to the neocortical structures. And the inputs of that is coming from the two structures, and that is the medial septal nuclei. Another one is the nucleus basalis of Meynert. And so what happened is that these information they have, these two structures, they have profuse and diffuse projections to the various areas of the neocortex, as you can see by the many arrows that's coming here. And then so these informations are going to project to like the pyramidal neurons that you see in the neocortex, and then this is going to help them generate um, memory by raising its activity. And what do I mean by that? Let's take a look in the next slide, you get a better idea. So it turns out that, let's say, a pyramidal neuron that would usually kind of fire in this method. You can see that it kind of fires in clusters. But when you apply acetylcholine to it, or norepinephrine, you can see that the spikes of that, it becomes a little bit more efficient. Okay, and then what happened is that when you have structure damage to the basal forebrain structure, and then the basal frame was not able to release a lot of acetylcholine, then this is going to result in severe episodic memory functioning. Okay, so now let's take a look at what these words are saying. Okay, so acetylcholine provide important mechanism for cortical synchrony and desynchrony of the cortical neuronal populations. Okay, and it also play a very important role in neuroplasticity. And now, and this is also now one of the things I do want to talk about it, and this is also rich in nitric oxide, and this is regulated during sleep. Okay, and this has to be a very important aspect of memory consolidation during sleep. And on top of that, nitric oxide is also a neurotrophic factor. So now, without that, the neurons in the cerebral cortex is not going to function very well in the sense that it's going to start to go through some program apoptosis, which means that these neurons are going to start to degenerate, which is not a good thing when you kind of want to preserve all the neurons in the brain. Because as we know, most neurons in the brain, once they die, they do not reborn. It's not like your liver that they can be regenerated. The only exception to these places are the olfactory bulb and also the dentate gyrus and the hippocampus, where we see adult neurogenesis. And other than that, we do not see any evidence of adult neurogenesis elsewhere, unless in some very dramatic or genetic diseases that are out there. But usually, when you have like genesis that's going on in the brain, it's not good news because that usually says there's some sort of neoplasms, which means that there might be cancerous or malignant cells that's going on in your body. So that's not what you want either. Now, one of the things about Alzheimer's disease is that this cholinergic projections and the overall cholinergic cells are very low. Okay, and then when we kind of think about it, might be the reason why the cortex is not able to do its job in modulating the activities and also form a very strong neuroplasticity, which is pretty much the anatomical or physiological correlates when it comes to the actual learning and memory aspects. Okay, now in Alzheimer's disease, what you can kind of think about it is it counts for more than half of the senile dementia. Okay, and familial forms. Now it comes in many forms, but the familial form of Alzheimer's disease is linked to mutations in amyloid precursor protein or APP. And there are two genes, which is presenilin 1 and 2, and there's another one that is apolipoprotein, and which is more related to the late onset. And so what happened with that is that these two genes are going to collectively form to something that is going to contribute to something called the amyloid protein, which is going to form a lot of tangles and which disrupts the cell communication from one another when it comes to and this is going to prevent the proper working of the cerebral cortical neurons. Now let's take a look at the pathogenesis of Alzheimer's disease. Okay, what happens is that there are going to be a lot of loss in the nucleus basalis of Meynert, the hippocampus in the neocortex, the locus coeruleus, the nucleus of Raphe, and also in the hypothalamus. Now, the most important things are the nucleus basalis of Meynert, that is the loss of the cholinergic neurons, and also the decrease of cholinergic projections from these nucleus cells of Meynert to the neocortex. Okay, now so that's the first level. The second level is that there's going to be a lot of beta amyloid protein plaques that we kind of mentioned in the previous slide. And then the second one is going to, and so the third one is going to be the tau-containing intraneuronal neurofibrillary tangles. And then so what these are all doing in the beta amyloid plaques and also the tau-containing tangles, all of these are going to disrupt the synaptic connections that is going on in the brain. And so now one of the things that we really know about synaptic connection is that it really is the cellular basis of learning in the brain. Without all of these new synaptic connections that are being formed, as what you have seen previously in the modal learning lectures, well, it's not only in the case of modal learning, but learning in general is it really requires new synapses that are being inserted into the circuit. So what happens is that these memories are not able to be learned in Alzheimer's disease, and then what is going to happen? Then what you see the result of that is dementia. Okay, basically. Okay, now the plaques and the tangles are the best cellular markers in AD, and what you are basically seeing in these arrows, so here and also here and here. So these are the plaques and tangles are basically that is disrupting the transmission of synapses that's going on, and also that prevents new synapses being inserted into the circuit. And uh, these are actually the brains that is coming from patients that have passed away from, well, not usually from AD, but also but usually from something else. Okay. Uh, so then you can see that these patients' brains are really not in good shape in this case, because with these tangles and plaques are present, then a lot of these neuronal connections are being disrupted. And then what happens is that when these neurons cannot transmit signals properly, they are going to start to die off. And then this is why you see a lot of atrophy in not just in the cortex, but also in many other areas of the brain wherever these brains and tangles are really present. Okay. Okay. So now as you can kind of think about it, that the healthy neurons are the prerequisites for a healthy brain. So now we have talked about basically many aspects when it comes to the healthy the brains. In the Alzheimer's disease, what we see is the plaques and tangles, and in Parkinson's disease, we didn't have time to talk that much about it in the motor sections, but and there is something called the Lewy bodies when you look at the brains of the Parkinson's patients, and then in Huntington's disease, what you can see is a lot of something called the intranuclear inclusions. And in prion amyloid and in prions disease, what you can see is there are a lot of the amyloid plaque as well. And in the ALS, which as you might also know as Lou Gehrig's disease, and they have a lot of the corrosive aggregates of this. And so what we're basically saying that without the proper adequate communications that's going on in the neurons as a whole, then there are going to be a lot of problems for normal brain to function pretty well. Now, what you can kind of think about when it comes to a brain that does not have adequate amount of cholinergic input is that the left brain here is the CT of the actual Alzheimer's disease patient, and then so you can see that here, okay. And then the one on the right is the adult, and that's basically an age-matched control. And you can basically see that what does this look very similar to? This looks very similar to the Korsakoff's patients that you saw in the previous mini slides, right? You can see a lot of cortical atrophy. Right? You can see that, all of these areas here in normal patients, you don't see that much, but in an Alzheimer's patient, you see that, oh my God, the gray matter are basically gone. There isn't that much cortex that's going on. Look how big the temporal sulcus is, the central sulcus. It's very big, okay, in the Alzheimer's patients. So what you kind of want to think about it as these anatomical changes really is a form of result of neural connections and inadequate amount of cholinergic input. Okay, and postmortemly, what you basically can look at Alzheimer's patients and also a non-Alzheimer's patients, human, you can see that the normal brain here, and this is an AD patient's brain. Okay, so the AD patient's brain, you can see that there are a lot of hollow here, and then the brain in general is smaller, and then the volume and the brain volume is also going to be smaller. You can see that there's a lot of atrophy in the Alzheimer's disease patients and not so much in the normal age-matched human patients that did not die from Alzheimer's. Was not diagnosed with Alzheimer's. Okay, basically, so that concludes today's lecture, and then the next lecture we'll talk about semantic memory, and then we'll talk about the physiological aspect and the cellular basis of learning and memory.